binomial distribution. So let's look at some examples. So let's say let's say you draw 7 cards with replacement. You draw 7 cards with replacement, and what I want is the probability of at least 5 hearts. What is the probability of at least 5 hearts? Yes, we show 1/4. Yes, but there's more to it.
Then you have to go second one. 12 out of 52.
With replacement.
Oh.
So how do you do
12 is 2. Because once you take it out, you can't put it back in.
with replacement? It's Monday. We all feel that way. Imagine how I felt when I parked my car, looked at in my book bag, and there was like homework once. I'm like, I left them on the dinner table. So I know the feeling. But how did we do binomial distributions? Right? How do we do probabilities? First of all, what were the things? We had an n, a p, a q, an x, and a p of x. Right? N was the number of trials we had performed. P was the probability of success in a single trial. Q was the probability of failure in a single trial. X was the number of successes we were hoping to get out of all those trials. And P of X was the probability of getting that number of successes out of all those trials. Yes? Everybody remember that? We kind of covered it long time ago. That long? So in our case, N would be 7, P would be 25%, right? Why? Well, because I'm going to say success is picking a heart out of a deck of cards, right? This is how I define success. Success is picking a heart, right? We are talking about hearts, so Q, well, Q would be, Q is the complement of P, so that's that. X, you're saying X is 5. So when you go to the bar with your mates and you say, I'm going to have at least 5 beers, you walk out with 5 beers in you? Okay, how about it's an open tab, right? You don't have to pay. Is it going to be 5 beers? Well, it's going to be 5 or 6 or 7, right? Now, I'm going to put pluses here. I'm just going to go, let's put commas. 5, 6, or 7, right? At least 5 means 5 or more. And since 7 is the maximum, it's 5, 6, or 7. So what's P of X? It's the probability of 5 plus probability of 6 plus probability of 7. Now we can try to do this the way we have been doing it before. We could try doing this way. But honestly, this is going to take a lot of time if we do for all 3 of those. So the other way we dealt with this was using the table. Everybody has a table? Yay.
We can use the table on our quiz, right?
On the exam, yes. But you won't need it for exam 1, because
Oh, for the next one. Oh, yeah.
for the final, right? Or if we decide to do exams more often, right? Right. Anybody else forgot a table? I thought you swore that you're going to. It's okay. I killed extra cheese just for you. All right. So how do we read this table?
Well, N is 7.
N is 7, right? So the most left column. And then we are looking at 5 out of 7 at 25%. So we look at 25% on top, or 0.25. And we're looking at 5 out of 7. And what do we get? No. 0.012.
Yeah.
So this is 0.012. 6 out of 7 at 25%, which is the one number below that. Yeah. And the last one? 0. Is everybody comfortable reading the table? It's very important. You guys good? Okay. So, all right. So this was easy. That's 0.0. Oh, sorry, 0.001. All right. Let's do more.
Is that percentage, right?
No, the percentage would be 1.3%. This is the decimal. Exactly 4 hearts. And let's go probability of at most 3 hearts. Probability of more than 2 hearts. And probability of yes, that's the same. So if we look at the next one, it's exactly 4. Right? Again, if you want to be precise, the whole formula, right? But if you want to speed up the process and look at that table, it comes from the table. And if we look at 4 out of 7 at 25%, for this one, at most 3 means P of 0, P of 1, P of 2, and P of 3. So you have to add 4 numbers. So you just pick the column and you just start adding things. And I came out to be 0.244. I believe you should have a very similar answer.
Are we still looking at the same column?
Yep. It's the same example. I added probability of 0, probability of 1, probability of 2, and probability of 3.
Like, it's 0.311.
Yeah.
Yeah, 0.311.
the first one is 0.133, right? Then it's 0.3. Oh, okay. Sorry, I I copied the wrong one. You're right. Should be 0.928. Sorry, I was meaning to. Sorry, it misread things. Thank you for catching that. Okay, fine. Gold star. All right, but at most 3 isn't the interesting. This one is interesting. This one is interesting, and this one is interesting. Why are those two interesting? They're the last two.
More than 2. You still got 2, 3, 4, 5, 6, 7.
Because I can look at the complement of it. What's the complement of more than 2?
2, 5.
Well, more than 2 means 3, 4, 5, 6, 7, right? Less than 3 or 2 or less, right?
2 complement of.
So the complement of that is the probability of what? Well, of 0 plus probability of 1 plus probability of 2. Yes, that's the complement. Complement. Right? Complement means everything but. Right? So if you're looking at more than 2, we're looking at 2, 3. Sorry, we're looking at more. So we need plus.
Oh, it would be 3, 4, 5, 6, 7.
Yeah? So the complement would be 0, 1, and 2. Yes? There is less numbers here than here. So 1 minus the complement would give you this. Right?
That would complete 1 if you added it together.
If you add all the probabilities from 0 to 7 together, they should come up to 1. In some of the cases, they will come up to 0.999 because they are rounded, but they should come up to 1. So if you can approach it forward, or you can try to approach it backwards. An easy example is that somebody gave me last class was shooting a gun. Right? You have 14 bullets in a magazine. You can either count 10 shots, or after shooting you can take out the magazine and count how many bullets are left. Right? You have one or the other choice, because total what left and what shot has to be 14. Same with this one, less than 6. So it's 1 minus probability of less than, so probability of 6 plus probability of 7. Funny thing with the last one. If you do it this way, you're going to come out with 0.999. If you do it forward, you're going to come up with 0.998. So you're going to get two different answers. They are going to be very close, but they're going to be different. And I accept both. As long as you show me how you got there, I accept both. Okay. Well, easy, fun things. So today we're going to do the mean variance and standard deviation. We've been so excited about this. I thought about it all weekend. So let's start with the first one, the mean. If you were going to flip a coin 10 times, how many heads would you expect to get? 5, right? So the mean is the number of trials times the probability of success in a single trial, right? So the number of successes you expect to occur from your procedure. 2, variance. What is variance? No, what is variance when I talk about variance of a data? Yes, no. Something more. More.
All the data in between.
No. We had a way to measure how data is spread apart, right? One more way to do it was range, the other one was standard deviation, right? Variance is a part of standard deviation, right? It's square of standard deviation. So when we're looking at variance, we should be looking at what? Well, we should be looking at how the data is spread apart. Well, how much data we have matters. What's the success rate matters, right? Because the more successes you have, the more the data will be clumped up around the mean. And then it also matters the failures. So variance is calculated by this formula, NPQ. And the last one, standard deviation, is square root of that. So NPQ square root. So here's the question. Why am I using population symbols, not sample symbols? Why am I using population symbols, not sample symbols? Right, before that we used means, we had X bar, and we had mu. But here I'm using mu. Why?
You look at the whole range. That's the exception.
You have a sample, you use the whole population.
Why? Why am I using the whole population and not sections of it?
Because the NPQ is the whole population.
No. No, because the number of trials in a binomial distribution is fixed. Right? We have a fixed number of trials. Fixed means countable. Might be a very large number, but it's countable. So every time I'm dealing with it, I'm dealing with a population. Like I'm taking this section, this is my whole section. That's why we're using mu and sigma. I'm just waiting for the crickets to queue in. Okay. When we're talking about binomial distributions, we're talking about 4 things that are happening. One is it's a fixed number of trials, right? They're independent, so they don't affect each other, right? Probability of success stays the same across all of them, right? So when I have a collection of data, because I'm going to have to look at all of it, I can just say that this is population, right? If I get a list of surveys back with question, yes, no question, right? Success and failure question. I'm going to look at those surveys as a population, not all the people that could have given me surveys didn't give me surveys. I'm going to look at the surveys that I got. That's why we're using mu versus x bar, right? Because we have to talk about a fixed number of trials. There's a countable number of. There's not, oh, we're going to get a survey in. No, I'm going to take a look at all of them, and this is what I'm going to deal with. Imagine if you had this table going on forever, right? And you're collecting your surveys, and you collected 500 surveys, and you're trying to do calculations on something. And then somebody decides to bring survey 501. Does this change where you're looking at the table? Right, if you go from 6 to 7. So the moment you collect and start looking at distributions, this is your population.
But when the population changes,
Then you have to do the whole thing from scratch. There is no little adjustments. So that's why we're looking at population. Right? So when we're talking binomials, binomial distributions, we get, and what we get, we take and we deal with that. Okay. All right, let's look at an example about this. So the example we're going to take a look at. The example we're going to take a look at. So a certain town is made up of 80% A and 20% B. We're going to be selecting a set of 12 people, and we need to find the mean and standard deviation. What's 12 people in a room? Twelve people in a room is a jury. Right? Connections. Need to make connections. But yes, in this case, 12 would be the population. But it's a binomial distribution. How do we start binomial distributions? We start binomial distributions by talking about what we consider a success. Right? We have two outcomes, success and failure. So let's talk about what we would consider a success. What would you consider a success in this case? Okay. Selecting a person versus a goat.
being selected and not being selected.
We have this data right here, right? If we have a town that is mostly made out of A and not B, we would expect the jury to be mostly made out of A, not B. So how about we just say success is selecting an A person, right? Somebody from this population. Right? Randomly selecting an A. That would be a success. No? Maybe?
Well, then that means if you select a B person, that's a failure, right?
Yes. Could we, so in this case, success would be this, and failure.
I thought part of the success would be picking a person or a B person.
Out of what?
Out of the
Out of people, right? But that means that we have something bigger. We have A, B, and the rest of them. Let's call it C, right? Here I have very specifically A and B. Think of a bag of marbles, right? You have to pull. We can take a look at it this way, or we could take a look at this way, right? Whichever way you pick, that doesn't matter because P and Q are complements of each other, right? right? In this case, my n is equal to 12, my p is equal to AD, and my q is equal to 20%. Okay? In this case, my n is 12, my p equals to 0.2, and my q equals to 0.2. Because at the end of the day, I'm asking about the mean, and mean is the number of successes I'm expecting, right? So I'm expecting a success. So if I have a group of 12 people pulled out of this town, I'm asking you how many of A's and B's am I expecting? In this case, mu equals to n times p, which is 12 times 0.8, which comes out to 9.6. And here, mu equals n times p, which is 12 times 0.2. That comes out to be 2.4. It's a lousy two. Right? Now, the mean is a number, but the mean has a meaning. Here, the expected number of jurors A on a jury of 12 is 9.6 out of, let's say, ethnicity A. If we consider B being a success, because we want to have more minority on the jury, then we consider that we are expecting at least 2.4, right? At least 2. On the other hand, variance and standard deviations are talking about how the data is spread apart. Regardless if we are considering one or the other success, the data is still going to be spread out about the same way, which means that when we consider standard deviation, which is square root of npq, that's square root of 12.8.2, which equals to, in my case, 1.39. It's equal to 1.39 in both cases because it takes into account both P and Q. So regardless if I switch them around, I still get the same answer. Questions? So far, everybody is with me. So I'm going to focus on case number 1, because this one makes sense to me more. Right? If it's a bigger A population, I'm going to expect more A's on the jury. Calculating means and standard deviations is not the goal of this class. The goal of this class is what number of A's would be considered usual? Because I'm assuming nobody is going to try to put 9.6 of a person on a jury. Right? That 9.6 means what? Means if I keep on picking juries of 12, and across all those juries of 12, I average number of A's, I'm going to come out with 9.6. Right? But 9.6 is not number of jurors of A on a jury of 12. 9 healthy and 1 came mostly chopped up. Okay, but here's the question: what is a number of A's that we would consider usual? What's usual? We will do standard deviations, right? So we would look at the mean, and mean plus 2 sigma, and mean minus 2 sigma. In our case, that comes out to be 682 and 12.30. 9.6 minus 2 times 1.39 and 9.6 plus 2 times 1.39. Another question is 12.38 making sense?
You already have 12.
Yes, but this 12.38 is a boundary, right? Which means that we are expecting between, on average, between 9.82 and 12 jurors to be of A, out of A, right? This is coming out of what we are going to be picking, but that's okay. Just means that we are okay with 12 of the jurors being A. So far, so good. Okay, let's blow this question up, make it bigger. Let's say over a period of time, 870 people were selected for the set of 12. Find the mean and standard deviation and find the usual range.
So we're still using the 80/20?
Oh, it's still 820. It's still the same town. Just this time we have historical data. We are not talking about abstract 12 people and how many people are. We have actual. Over 10 years, we had 870 jurors getting picked. I'll move it over here so we are all over a period of time. 870 jurors were picked. Again, what's our N? 870. Right? The 12 is there to confuse you. We don't care that they came in packets of 12. We're looking at all the jurors being picked. P, I'm still saying this is mostly an A town, so selecting an A makes sense as a success. Well, failure is selecting a B. Now what's the mean? N times P, which is 870 times 0.8, which comes out to be 696. Standard deviation is NPQ square rooted, which comes out to be 870.8.2 square root, which means that our standard deviation comes out to be 11.8. So what would be our usual range? Well, our usual range would still be 2 standard deviations, so mu plus 2 standard deviations, and mu minus 2 standard deviations with mu in the middle. This is 696. In our case, this will be 719.6 and 67. Questions? Everybody comfortable how I got there? Ask now, because there's no way you're going to forever hold your peace. I am going to get down to it. I'm just going to find your limit. So I did 696 plus 2 times 11.8 and 696 minus 2 times 11.8. I got those two numbers. Okay, we're happy with this result. So out of 870 people, we're expecting 672 to almost 720 of them to be A. Okay, let's make this real. Let's make this real. So let's say actual numbers. I'm going to put in quotation marks because actual numbers, I'm going to gently adjust them so they come out nicer. But let's say actual numbers. Let's say we have a town with 80% of the population being Mexican Americans or Latino. And let's say 20% being white. Let's say we have a town like this. And what happens if I told you that over 10 years they picked 870 jurors and 275 of them were Mexican Americans or Latino? What do you do with this piece of information?
That's the medium, right? 275.
No, this is the actual number.
So,
I'm saying
I'm trying to figure out.
I'm having a town that has the same composition it had before, right? And I'm telling you that over 10 years they picked 870 jurors. And I'm telling you out of those 870 jurors, 275 were Mexican Americans or Latino.
So the population minus?
Hang on, right? Well, the question is, what do you do with this number? What does this number mean?
You have to find, well, you have to look at the change in Mexican.
No, I'm telling you, this is what it has been forever. This is a New Mexico town close to the border.
Plug in 80% to 275 to figure out the Mexican population.
No, this is Mexican Americans or Latinos already picked.
so white would be just 1 point.
No,
No, out of the
no. Okay, we were talking about abstract jury, right? Out of 870 people, we were expecting to be usually between 672 and 720 Mexican Americans or Latinos in that jury. And I'm telling you the actual number says there's 275 of them over that period.
Oh, that's,
How unusual?
It's not in those numbers.
no, that's using white Americans.
No, this is saying, this is using this town, A and B's.
Yeah.
And I'm telling you A is
Oh,
Mexican Americans and Latinos.
oh.
I'm talking about a town close to the Mexican border which is mostly Latino, right? Or Hispanic, or what, however the proper term is.
Sorry,
You know,
okay.
I'm sour cream and apparently a haole, so.
That's an outlier.
Okay, outlier, unusual. How unusual?
99.9. Oh, that's 99.99.
Not good enough.
Because it goes way
Not good enough.
beyond-
How unusual is this? Well, look, it's supposed to be about 700. It's a third of it, Close enough, right?
No, because it's beyond the two.
How unusual? I want a number. I want something. How unusual is this?
Oh, you have to find the deviation range.
How do we do that?
Uh,
What's that equation? How do we do that? What's that equation?
deviation.
I'm asking.
The deviation is 11.8
Yes.
divided by 275.
No. No.
275 or 11.8.
All right. In chapter one, we covered something. We talked about that there is this thing that tells you how rare a piece of data is. That thing was called the z-score. Right? How many standard deviations is that piece of data away from the mean? Yes? If it was within 2, which is goes from -2 to +2, that was usual. If it was slightly wider, right, we consider it rare at about 3. And then I told you gently that if it goes beyond 5, either way, we're getting into this abstract realm because very few things get this rare, right? We talked about 6 sigma as being the super efficient way not to have mistakes. So how rare is this? Well, the z-score has this formula, x minus mu divided by sigma. In our case, that will be 275 minus 696 divided by 11.8. So the z-score would be equal to what? Yep. You have a better chance of getting hit by a big-ass meteor, going to the hospital, giving birth to another Jesus, getting hit on your meteor, getting back home, and still cooking dinner. -50 doesn't happen. I'm not saying it's impossible. I'm saying at 6 or 7 I get worried. At 10 we assume that it's almost impossible to do. Right? If I tell you, hey, this is what you expect, this is what you got, I'm doing this very simple calculation. I'm not hearing the argument, well, this is 1/3 of this, so yeah, they got underrepresented. I'm saying this is not happening randomly. The jury isn't picked randomly. Because randomly, this is 50 standard deviations away from the mean. At 6 standard deviations, we are getting into this realm of 3 out of a billion. Right? So when you get, right, this class is about decision making, right? Public administration. The math part is easy, we can get here, right? And then you get an actual piece of data, and because you know how to get this, you suddenly can start asking questions, where the hell did you come up with this? If I didn't know about this and somebody gave me this, first assumption would be, okay, maybe they mean, maybe they mean a working marker. Maybe they mean this, right? That would be my first assumption. If somebody gives me this on a homework, or maybe they mean this and they're trying to tell me something is really, really rare. If you still insist this is it, I'm telling you that this wasn't random. The chances of this being random are slim to non-existent, right? So if you have a jury that is mostly white in a town that is mostly Latino, once, okay, unusual, but okay. Maybe they're just over 870 people were picked and you still get that preference. I get very worried, right? This class is about, for all of you at some point, this class is going to be about, hey, why is this not adding up with this? And how can we deal with this? Right? This is telling me something. Right? If you're doing auditing of elections and somebody tells you, well, it's 0.5 standard deviations away, okay, you know, we weren't expecting, some people misvoted, happens. 5, you say it's impossible, we screwed up somewhere, either predicting or doing the exit polls or polling, we did some big mistake. You say that, and then somebody handpicked people out for the election. Because randomly, that's not happening. Okay. So moving on. What are you coming up with? 216, what 216? You're probably doing this minus this divided by this. Do the subtraction first and then divide. If you just plug in all the things in line, you're going to get the wrong answer. All right. Sorry? 35, not 50?
Yeah, 35.6.
Okay. 35.6. Still freaking impossible. Well, I'm not saying impossible. Okay. I'm not saying impossible. Maybe, across the universe before the Big Bang, when the civilization was still here, that happened, But no, 35 is just as bad. Hell, 15 is just as bad. Anything above 5 or 6 is just plain insane. Okay. 35. Huh. 35. Okay. All right. I'm assuming you guys want more, so let's do more. I see the excitement. So we're going to start looking at since discrete random variable has only so many things we can do with it, let's look at continuous random variable. We can still graph continuous random variable. We can still do it. So if the continuous random variable, I'm being lazy here, has a symmetric bell shape curve, it is considered to have a normal distribution. Symmetric bell-shaped curves, normal distribution. What we are going to try to do is, when we had discrete random variable, we knew all the numbers. We could deal with all the numbers. Now we are running the problem where a continuous random variable, we have a lot more choices. So getting those really well-defined cut lines isn't very obvious for us. Right? But what we can do is we can start looking at probability and area the same way. Right? If you had this piece of paper and I told you to cut 0.7245% of this piece of paper, could you do it? You could. You could measure it out and take a very thin slice out of it, right? If I told you to take 52.749% of this piece of paper, you would find 50%, you would shift it over, you cut it. We can do it, right? So we can start looking at at probability and area in a very similar way. And before we start to do that, we're going to start looking at something called uniform distribution. Uniform distribution. In a uniform distribution, all values have the same probability. Have the same probability of occurring. Okay, let's look at an example. How long is this class? Well, it's 80 minutes, right? Have I went over and taught this class longer than 80 minutes? Yes. Have I taught it shorter than 80 minutes? Do you know how much this class is going to take today? Are we going to stop at exactly 80? Or is it going to be 80 and a quarter of a second later? Right, where is this stopping? So let's say we look at our finish times between 75 minutes and 85 minutes. Let's say I don't overrun 85 minutes and I don't underrun 75 minutes. And I want to talk about uniform distribution. I'm going to say, hey, this class lasts 80 minutes plus minus 5, right? But at any day, the probability of me finishing somewhere between 75 minutes and 85 minutes is the same. Do you know how long the class is going to be today? If you take a wild guess. Right? Now? No. That's a no. Right? So each one of those times will have the same probability of happening. Right? I know it, you don't. You don't know how much of those yellow pages I'm going to flip before we finish. So if I wanted to equate this area to probability, we know probability is between 0 and 1, right? Class is going to finish between 75 minutes and 85 minutes, which means that the probability of class finishing is somewhere here, right? So the area of this, we're going to force it to be equal to 1. If we force this area to be 1, right, what's the probability we're going to finish at any given time? Well, this is this side is length of 10, right? Times this side has to equal to 1. So this side has to be 0.1. Right? This needs to be 0.1 because we need the area to be 1. Right? Because we are forcing the area to be 1. Because if it's 1, we can equate it to probability. Right? Okay. Can somebody tell me what's the probability of exactly finishing right here? Exactly there. What's the probability of finishing exactly here? Doesn't matter. I can give you a number, but doesn't matter. How? Exactly here is a line, right? We just said probability is area. We are equating probability to area. What is the area of a line? Well, it has some height, but does it have width? No. So we have height times width, so some height times 0, 0. So the probability of it finishing here right? How do I get 0? We have infinite number of possibilities here. if I choose one of them, right, that's 1 out of infinite. 1 out of infinite is going towards 0, right? Okay. If we cannot look at this because we're looking at probabilities, we should probably start looking at a range. Right? We could deal with a range because range will have a height and a width. So let's take a look at this. So what I say here, I said one area must equal 1 and 2 so area must equal 1 and height for each value must be somewhere between 0 and 1. Right there, each value cannot have more than 100% chance of happening. Okay, so we have this. So, well, let's find probability. Class is going to end between 8.82.5 and 85 minutes. What's the probability of that? My probability class is going to end between 82.5 and 85 minutes. In. So let's take a look at it. Well, we have this. This is 85. This is 75. 1. Area equals to 1. Where's 82.5? This is 80, so 82.5 is somewhere here. Yes? So what I'm looking at is asking is what's the probability we're going to end in that range, that region? Closer, yes. Well, we don't know, right? But we know we're dealing with area, right? We said, hey, probability, we're going to force area to be 1 so we can equate it to probability. So what's the area of this little section? Well, this area is 85 minus 82.5, right? That's the width of that box. And what's the height of the box? 0.1. So times 0.1. Right? That area is this. This is what? 2.5. 2.5 times 0.1. 0.25. Right? The area of that rectangle is 0.25. Which means that if area is equated to probability, the probability of finishing the class between 82.5 and 85 minutes is 25%.
And it always has to be 0.1.
Oh no, in this case I made it 0.1 because I had a whole 10 ticks here, so I need a 0.1 because I want to force the area to be 1, right? None of the probabilities can be bigger than 1, right? And the area needs to be 1. Okay? Even though we cannot tell the probability for exactly ending at each given time, right? We can start talking about probability of a range of options, like a width of the box. Yes. Yeah. Well, so how many times are there between 75 minutes and 85 minutes? How many different ticks you can do? Well, we could go by the minutes. So we go 75, 76, 77, 70. But somebody could say, hey, 75 and a half, 70, right? And then you can go atomic clock and vibration of cesium, and then you can go vibrations of mercury under condition X, Y, and Z, right? And you can do splits, right? We are talking about continuous, which means that there's infinite number of possibilities between, right, between the points. Infinite number of possibilities, which means if I ask about a specific one, it's infinite, right? If the deck of cards was the size of infinite, pulling one specific card out of the deck would be 1 out of infinite, which is 0 for all purposes. Okay. More? More. More. I can see it in your eyes. All right. So let's follow that normal distribution. If we look at distributions, normal distributions, we run into some problems. Because everything that has a symmetric bell-shaped curve, that we call normal distribution, is surrounded around the mean, which means that we could run into problems like this. Here you go. Two normal distributions. One has a mean of 63.9 with a standard deviation of 2.1. Right? The data isn't very spread around because the other one is mean of 69 and a standard deviation of 2.8. Right? They would be centered differently. They would have slightly different shape. Both of them are symmetric, and both of them are bell-shaped. Right? I'm trying to talk about area equals probability for a uniform distribution, which is very, very easy. Right? It's a rectangle. Here, I could find the equation for this graph, and I could find the area underneath this graph, and I could possibly force it to be equal to 1. But that means for every set of data that has a normal distribution, I will have to do this all over again. And that's a problem. How many of you want to do these calculations over and over again, right? Remember binomial distribution? After a while, you're like, hell, there's a table. I really don't care to do this thing. So, what we did in statistics, well, as in I take the credit for all the great thinkers before me, we said, hey, we have standard, normal distribution. Wouldn't it be awesome if we could get all of those to look the same? Yeah. So we can actually look at the data. So we have standard normal distribution. And standard normal distribution looks like this. And the means are great, you know, and every mean is important. But wouldn't it be awesome if the standard normal distribution was centered around 0? Just saying, right? 0 seems like a good place to be. Right? This way we know if it's negative, we know if it's positive, right? It's nice. What else? What do we deal with? Oh, we deal with a lot of with that thing, that canon. What is it called? Standard deviation. Wouldn't it be awesome if we could say, hey, standard deviation is 1. Right? So I'm saying, hey, we want mean to be 0. We want standard deviation to be equal to 1. And here comes the last one. And because we just found out that having an area instead of to deal with probabilities, right? Instead of doing probabilities on something that is very, very small, we can actually say, hey, we can deal with ranges. Wouldn't it be spectacular if we could force the area to be 1 as well? And this is what standard normal distribution looks like. Standard normal distribution looks like this. Remember the empirical rule? (68). 68% will be here. Yes. And between those two, 5. This will be 95% of the area. And then -3 to +3, that will be 99.7%. Now this graph goes out to infinity. So if we wanted to take 100% of the data, we would be looking at something from negative infinity to infinity. So we're looking at all of it. The problem is, this would be awesome, but not every normal distribution has a mean of 0 and a standard deviation of 1. Right? We're going to do a couple examples on Wednesday that we got lucky, but they won't be happening this way. So we need a way to force a normal distribution into a standard normal distribution. And we have that really cool mechanism. The mechanism is called the z-score. Z-score will take a value like mu and turn it into 0. If x was my mean, then it's mu minus mu divided by standard deviation. That's 0. Right? If I look at a piece of data, let's say x is 1 standard deviation away from the mean. X is 1 standard deviation away from the mean. If I plug in this x here, what do I get? Well, I get mu plus sigma minus mu divided by sigma. Right? The z-score for this x is this. What is that? Well, it's mu minus mu, 0. Standard deviation divided by standard deviation. No. So if my x value was 1 standard deviation away from the mean, it's at 1. Right? So z-score is making normal distributions into standard normal distributions. Which means what? If it's standard normal, that means area and probability. Means we can go between area and probability. And again, as before, somebody sat down and did the calculations on the area. And now we get to use it for probability. Right? This class won't be covering how we get the actual formulas, but we can enjoy the results of those calculations. Right? And that is going to be on Wednesday.